In today's video, I'm going to be showing you how to use I2C on a Raspberry Pi and using the pigpio library. I will be using an ADXL 345 accelerometer, which uses I2C for command and reporting of data values. The ADXL 345 accelerometer used today is part of the Viam Rover that I have used in previous videos. This will allow me to focus on the I2C communication and allow me to verify the data reads from the Viam application itself. The first thing we're going to do is just show you the values being output from the accelerometer using the Viam server application. So as a reminder, the Viam Rover is tied to software developed by Viam, and it provides a web interface to show what is happening on the robot itself. With the vehicle just sitting flat on the table, we see a value of Z is positive 9.5, and then we say close to 0 for X and Y. If we turn the robot to its side, we see that the values change. So now X is positive 9.6-ish meters per second squared, Y is close to 0, and Z is also close to 0. So when we look at the Viam documentation, we can see it lists the accelerometer that they use, and they point you to the ADXL 345. When we read through the data sheet and we look at the pinouts, we actually see that this accelerometer has two different ways it can be communicated with. The Viam Rover already uses I2C, so we're going to use that interface today. Now, this data sheet is pretty complex. There's a lot about this sensor that you can learn. We're just going to focus on basic I2C communication and understanding how I can get the sensor to start providing data. When we look at the ADXL 345 data sheet and we find the I2C section, we see that there are two possible addresses for the accelerometer. One is 1D and the other is 53. So here we see this is the hardware diagram that's provided by Viam, and it doesn't easily tell me if that address select line is tied to high or low. So I don't yet know which address I need to be using to communicate with the device. However, there's a nice tool that we can use to figure that out, and I'll show you that a little bit later. What the Viam hardware diagram does show me is what lines are tied to the Raspberry Pi and the sensor. So we know which pins are on the Raspberry Pi are being used for the I2C interface. From here, we can see that the SDA line is tied to Raspberry pin 3 and the SCL line is tied to pin 5. If we then look at the Raspberry Pi documentation, we can see the Raspberry Pi names for those pins. So pin 3 is GPIO2 or SDA, and pin 5 is GPIO3 or SCL. So we know that the accelerometer is connected to the Raspberry Pi I2C lines. So we're going to be using native I2C on the Raspberry Pi to communicate with the accelerometer. If you'd like to learn more about I2C, I'll put a link to this good website I found, I2C-bus.org, that provides a good background on it. So I mentioned that the accelerometer can have two possible addresses, and depending on how it's connected or wired up, it'll be one or the other address. Now, we don't know how it is connected on the Viam Rover, so we need to figure that out. We could go and try to investigate the actual hardware connections, but that's a lot of work, and there's a little bit of an easier way to figure this out. So what we need to do is we install this set of tools called I2C tools. Make sure you include the dash in I2C tools, so I2C dash tools. And as you can see, I already have it installed. This installs a tool called I2C detect that you can use to detect addresses connected to your I2C bus. In order to do that, we need to figure out which bus or which buses we have available to us. An easy way to do that is to look at the dev folder. There should be a dev I2C device. So here we see there's an I2C-1 device, and that tells us that bus 1 is available. When we run I2C detect, we see that the address that responds is 53. So we know that the accelerometer is using its alternate address, which is address 53. Now that we've figured out which I2C bus is being used and we know the address of the device, we can go look at the pigpio library interface to figure out how we start communicating with it. So on the pigpio website, we see there's a section here for I2C, and there are a number of functions that are available to be used. As we look at the available functions, we can see that there are two that are obvious that we'll need to use. We need to open the I2C bus, close it when we're done, and then there are a number of read and write operations, which we will investigate a little bit more. So first we look at the open, and we see that we have to provide the bus that we're using. So our case, bus 1, the address of the device that we're communicating with, and then some I2C flags. But ICE flags are not defined, so we just set that to 0 and we're done. They highlight that there are two physical buses on the Raspberry Pi, 0 and 1. So here we see that I2C 0 is GPIO 0 and 1, while 2 and 3 is bus 1. And we saw that in the hardware and the Linux operating system as well. And then it returns a handle to that open connection. If it's less than 0, then we weren't able to open connection to that device for some reason. And then we just call close whenever we're done with that I2C connection, and we pass in the handle that we were given up here in the open. So now we need to figure out which registers we need to be reading and writing to in order to get the data. In the data sheet, we see that there's a long list of register addresses. And this address is register address, not device address. Those are two separate things. And we have a lot of description about the different registers. The ones that we are going to focus on today are the registers that provide the data, the XYZ access data. And then we're also going to have to communicate with some other configuration registers in order to configure the device to start taking measurements, and then we can read those measurements from these other registers. So in order to understand how to configure the device, we will look at this theory of operation section in the datasheet. And the most important part in here is this power sequencing section. We can see that after the device is powered on, the device enters this standby mode, and then it waits for the command to enter measurement mode to be received. If we don't do that, then the device will not start taking measurements, and anything you read from it will probably be zeros. The other thing we need to do is to configure the device. So the device actually supports a wide range of resolutions, and we need to make sure that we are using the resolution that we care about. Documentation says that it is recommended to configure the device in standby mode and then enable measurement mode. So we power on, configure the device, then turn on measurements, and then we can start reading values. Then we look at standby mode, and it tells us, okay, the register that we need to modify in order to turn on measure mode is this power CTL register. So we go back down to the register list, we will see 2D power CTL. So we need to modify that register in order to start measurements. The other register that is useful is this data format register, which lets us set the resolution. So we look at 2D and we see that here's what the register looks like. You can read about all the different possible values here, but the one we're going to focus on is this measure bit. We set the bit to 0 to put it into standby mode. We set it to 1 to put it into measurement mode. The other register that we need to look at is register 3.1, which is data format. The ones we care about here is this full resolution bit and these range bits. When you set the full resolution bit to 1, the device is in full resolution mode. And then range tells you the range. So here's the range of values that the sensor can be within. It can measure plus or minus 2G, plus or minus 4G, plus or minus 8G, and plus or minus 16G. And then the resolution bit tells you the resolutions. If you look at the specifications here, we can see the resolutions and the possible values. So this is important later when we need to convert from G values to meters per second. So let's go look at what this actually looks like in code using pigpio. So here's our standard application using pigpio functions directly. We disable the built-in pigpio signal handling like we've been doing for the last few videos. We initialize pigpio, And then we open up the I2C bus and get a handle to be able to communicate over the I2C bus. So here we're communicating with bus 1 and we're communicating with the device at address 53, and there are no flags, so we just set that to 0. We get our handle, we make sure that the handle is valid, otherwise we exit the application, and then we continue. For our example today, we're just going to configure the device in full resolution mode with plus or minus 16G range. So now to do that, we write to register 31 the values we care about. So here we need to set full res to 1 and the range here to 1, 1. Everything else we set to zeros. So here it's full resolution is 1, range is 1, 1 for plus or minus 16G. I have this helper function to write byte and make the code a little bit easier to read. The pigpio interface is this I2C write byte data function, and we say the handle, the register address, and the value. I then check the result of calling this function to make sure that it worked correctly and print out a message if it did not. The next thing we need to do after setting the resolution and range is we need to put the device into measure mode. 2D is a register for power control, and we turn on measure mode. So we go back to the datasheet and we look at register 2D, and we see that measure bit is bit 3. This is bit 3 here. We set that to 1. We leave everything else to 0. We check to make sure that that worked correctly. Otherwise, we have to exit the application. And now we are ready to start reading values from the device. As we saw, in order to read values from the device, there are 6 registers because the data from the device is a maximum of 16 bits or 2 bytes long. So we need to read both registers and then interpret them based on the resolution. When we look at the deeper description of those registers here, the output is 2's complement with data x0 is the least significant byte. So when we read from the data, whatever's in register 0 is going to be the lower side of my 16-bit value. It's also 2's complement, which means that it can be positive or negative numbers. So while we are running our application and we're in this loop, we're going to call this read 2 bytes function. And what I've done here is created this helper which reads just 2 bytes. So it's reading X, then reading Y, then reading Z as separate I2C communication operations. This function here is reading the bytes separately. This is not ideal because the measurement could change in between reads. So I'll read half of one measurement and then half of a second measurement, and I'm going to put them together as if they are one measurement, which isn't true or isn't necessarily true. This is for example purposes only. Do not do this. But in order to do this, I call this I2C read byte data function. I pass in the handle, I pass in the register address that I need to read. So in this example here, I'm passing in both the high register and the low register and then calling them separately. I read the low byte and then I read the high byte, and then I put them together to get the full 16-bit short value. I do that for X, Y, and Z. And then I must convert my integer value into the actual scaled G value. So from the datasheet, we can see that the full resolution of plus or minus 16G range is 13 bits. So we're going to be using 13 bits to represent all possible values within the 16 plus or minus 16G range. So when we go back to our application, we need to say 13 bits. That means there's a total possible number of values of 8,192. The measurement range is plus or minus 16G, which means there's 32G full range. So when we get this value, it's a scale integer value, we'll get an integer, and then we need to convert that integer into its double G value. So we say, hey, the scale for every one value change in the integer, it's going to be represented by this amount of change. So here we have 32 divided by 80, 8192. And that means that when the value read here is 0, then the measurement is 0G. If the value here is 1, then the value is 0.0039G, etc., etc. If the value here is 100, then the value would be 0.039G. So we take this value and we multiply it by the scale, and we get the value in G. Then we know G is about 9.8 meters per second, so that the meters per second value is the number of G multiplied by the G meters per second by gravity constant. Once we've done that, we can see the number of G and the meters per second being read. And we do that for all three of the axes. We just run this forever until every second we grab data from the device, and then we print it out, and then when we're done we close the bus and then deinitialize or terminate the pigpio library. So let's run this and see what happens. So we're running this and we can see that the value being printed out is just under -1G, which is minus 9.76 meters per second squared. And we'll see that the rover is still sitting on its left side, so the value here is as expected. So we flatten the robot, and then we see the Z value has gone to 9.5, 9.4 meters per second squared. Again, close to what Viam was telling us the values were when we were using it. So this at least shows us that we are reading values from the device correctly using I2C. Values might be slightly different from Viam because they probably have some calibration and offsets. We're not dealing with that today. We're just focused completely on, am I reading values that seem to make sense? And the answer to that is yes. Now, as we said, the reading individual bytes from those registers are not great. At the bare minimum, we should be reading individual words. Ideally, we would be able to read all 6 values in one go. So here in Accelerometer 3, we're going to use this I2C read, I2C block data function to try to read 6 bytes. Here we see this function, how we do it. We pry it in the handle, the start register, a buffer to populate with the values, and then a number of bytes to read. Read bytes, call that function, the handle, the register address. We're going to read 6 bytes from it, and then if it works, we convert the 6 bytes into our 3 shorts. So let's try that and see what happens. And we can see that the values are, again, as we expected. So the Z is about 9.4, 9.5 meters per second. Now, if you were looking at the pigpio APIs, you might also see this I2C read block data function and wonder what the difference between this function and the I2C read, I2C block data function is, right? The names are very, very close, really just I2C in the middle there. At least on the Raspberry Pi, this function does not work. And that's because this is not available within the kernel driver. And we can actually discover this using, again, the I2C tools function and I2C detect. So if you use I2C detect, there's a function with the F to tell you what features are available. We do that on bus 1. And here we can see SM bus block write works, SM bus block read does not, but I2C block read does. So we use that, and that's the distinction. In pigpio, this read block data is using this SM bus block read function, not Lily. And the I2C read, I2C block data is using this I2C block read. Like always, I like to wrap the pigpio functionality inside of my own library in order to simplify the application. This way, the application itself is easier to read, and a lot of the error handling can happen in the background. So for I2C, I did the same thing, and I created this I2C class to handle the communication on the bus, and it just wraps the pigpio library. Here we'll see that we have an open function. We pass in the bus ID and the device address. We've ignored the flags because flags aren't used right now. There's a close. There's a write, which can take a uint8 currently, and then a read, which can read a uint8 or a uint16 or a vector. So this simulates the read byte, read word, and read I2C block data functions, right? Those wrap those. I only added a write that takes a uint8 because that's the only one we're using right now for the accelerometer. So this is not intended to be full featured. This is just a minimum interface required to support this example. When we look at the actual code here, it's going to look very familiar, just like all our other functions. It inherits from device, and device is where we handle and support the initialization of the pygpio library and the disabling of the built-in pygpio signal handling. Then we also add some accessors. So just say, hey, tell me if the thing has already been opened. Tell me what the bus we're using is. And then what address we're communicating with. So when the thing is open, we can get the data from it if we need to in the future. We call open and then pass in the bus ID we're trying to open and the device address. And that just calls I2C open from the pygpio library. And then does error handling if there was some kind of error by throwing an exception that can be caught. Close is the same thing. Write is the same thing, wrapper around I2C write byte data, which we saw in the previous examples. Read with the UN8 wraps I2C read byte data. Read with the UN16 wraps I2C read word data. And then read from the vector wraps I2C read I2C block data. We use a vector here because we can set the size of the vector, and then what's happening is whatever the size of the vector is how much data we are going to read. So if you want to read 8 bytes, you create a vector of 8 bytes long. If you want to read 4 bytes, you create the vector of length 4. When we do that and we apply this to our application, we see that the application gets a little bit simpler. So we can open the connection, we can instantiate an I2C class object that we're just going to call ADXL345 for now. And then we're going to say we're going to open a connection to that device. Here's the bus. Here's the address of that device. And then we can write the resolution and range to it. We can start measurement mode, and then we can start reading data from it. In this example here, we're using the read short function to read in the individual XYZ axis values separately, and then we do our scaling here. However, the better way to read from the accelerometer is in that block read format, reading all 6 bytes all at once. So in Accelerometer 5, we do that using the vector read function. So we create a vector of UN8. We say the size of it is 6. So it's 6 values we need to read. And we say read from the starting address into this vector. And then we can convert the 6 bytes in the vector into individual values. One of the things to be aware of is all of the read functions in the libgpio library treats the data as UN8s. So you pass in a UN8 to all of these things, but if you know the value is signed, you have to cast it yourself back into a signed value. So here you'll see we're reading in UN8s, but then we convert those UN8s into an int16 so that we can treat it like a signed value. When we run this version of the application, it again reads values like we would expect. And if I manipulate the position of the robot, we see that the values change. In today's video, we looked at how to use I2C to communicate with an ADXL345 accelerometer. We primarily focused on how to use the I2C functions in the pygpio library and got some readings back from the accelerometer. We didn't dive too much into the specifics on how I2C works, and we did not dive into more complex functions for the accelerometer or talk about how to use any of the readings from the accelerometer, or even if the readings were calibrated enough for anything you might use. We focused primarily on how do I exchange data between an I2C device and the Raspberry Pi. As part of that, we did have to explore the a XDL345 datasheet and read through some of the functionality in order to get some valid readings and ensure that the I2C communication was working correctly. And I hope this helps. That's it for now. Talk to you soon. Later.